Good evening everyone. I welcome you all to the problem solving session of the NPTEL course on ice engines and gas turbines. I am Pradeev E. I am one of the TA for this course, and today we will see some problems on gas turbines and also finally a problem on compressors. So the first question is on the screen. For an extreme cases of propulsive efficiency of 0 and 100%, which of the following statement is correct? Option A, aircraft moving with higher velocity. Option B is no flight taking place. Option C is aircraft moving at a higher altitude. Option D is aircraft moving with lower velocity and higher altitude. So we know the expression for the propulsive efficiency. Propulsive efficiency eta p is given by 2 by 1 minus Cj by u. Here Cj is the jet velocity or the velocity of the exhaust gas. I would write exhaust jet velocity, and u is the velocity of the aircraft, or it can also be said that the air of the velocity of the intake air. Or some people call it a CA, which is velocity of intake air. Generally we assume that the air is stationary and the vehicle or the aircraft moves, and because of which we assume both are same, U and CA. So now if we take 0% and 100%, we can see what expression we get for C, J and U. So assuming NP is equal to 0, then that means 2 by 1 minus Cj by u is 0. And so here 2 is not 0, the numerator is not 0, so that means the denominator has to be infinite for this to become 0. So that means 1 minus Cj by u is infinite. Now that is Cj by u is infinite, or u is equal to 0, right? So this is one case where we say when the propulsive efficiency is 0, that means the velocity of the aircraft is 0. So that means no flight take place. Similarly, we can also see for the case of 100% efficiency, eta p is equal to 100% means 1. So that is 2 by 1 minus Cj by u is 1. Now if we solve this, this means 1 minus C, sorry, I think it is plus here. Now 1 plus Cj by u is equal to 2. That means Cj by u is equal to 1. So that is Cj is equal to u. So this is a condition for having 100% propulsive efficiency. Now we know that the propulsive force F is given by m dot into Cj minus u. So that is mass flow rate of air that is coming in into multiplied by the difference in the speed between the exhaust stream and the intake stream. So now if this Cj is equal to u, that means this thrust is 0. So that means there can be no the flight cannot will have not any thrust, so it cannot move. So again that means no flight takes place. So now we know this for the first problem for both the cases of 0% and 100% propulsive efficiency, no flight takes place. So that is the answer. Now going to the next problem. Consider the following equation. Please choose the correct expression A for propulsive efficiency. So we know propulsive efficiency is a function of is given by 2 by 1 plus Cj by U. So this is essentially a function of exhaust jet velocity and flight velocity. So now aircraft velocity or the flight velocity is given. The other expression should be velocity of the jet. It cannot be velocity of the incoming air because that is same as aircraft velocity. Velocity at the nozzle inlet, so that is some intermediate velocity in the gas turbine, and Mach number at the exit of nozzle. So these cannot be the answer. But if you try to derive this expression from this, it doesn't come. So the expression is not entirely right. But it can be it cannot be the function of these other parameters. It can be only a function of aircraft velocity and jet velocity. If you have any questions, you can ask me anytime regarding the problems. You can unmute yourself or you can put in the chat window so that I will know that you have a question. For multi-spool turbofan engine, the fan is driven by high pressure turbine, low pressure turbine, compressor, or none of the above. So it cannot be run by the compressor. So fan is a device which consumes work, mechanical work, and compressor is also a device which consumes mechanical work. So this cannot be an answer. However, for the turbine, it generates mechanical work, so it should be either of this turbine. Yeah, low pressure turbine is the right answer. So if you see a multi-stage gas turbine, it is generally C1, first compressor, and then it goes to a second compressor, so this is given to a combustion chamber, and then this is mechanically connected to a first turbine, or this is high pressure turbine, or I would write this as low pressure compressor or high pressure compressor. Then that is mechanically connected to a high pressure turbine, and then next comes the low pressure turbine, and this is coaxially connected to the low pressure compressor. So these two, there are two shafts, coaxial shafts here. Now for so this is called as multi-spool gas turbine engine. Now if the fan is there, then this low pressure compressor is replaced by a fan, and then that means it will be connected to a low pressure turbine. Which of the following options suits for aircraft handling? Higher mass flow rate for lower altitude flights. So options are turboprop, piston prop, turbojet, or both A and B. Can anyone guess the answer? Yes, both A and B is the right answer. Because the turbine prop and piston prop can handle more air mass flow, it is used for this case. Whereas turbojet are used in mainly for the fighter jets, where it has to go to a very high altitude and it will have very low mass of the vehicle mass will be very low compared to a passenger aircraft. Energy conversion efficiency of an aircraft engine is defined as we have 4 options. So in the denominator we have mass flow rate of fuel into calorific value, or mass flow rate of air into calorific value, then mass flow rate minus calorific value, or mass flow rate of air plus calorific value. Can anyone guess the answer? Option B. Yes, option B is right. The energy conversion efficiency is given by is generally output power by input power. So for an aircraft engine, the output power is a change in kinetic energy that it has imparted on the intake airflow. So that is kinetic energy change is the output power, and input power is fed from the fuel. So we need to have the fuel and fuel power in the as input power. So fuel power is mass flow rate of fuel into calorific value. So it depends upon the mass flow rate of fuel and not air. Sorry, I think then option B is not right. Option A is correct. The fuel power depends upon the mass flow rate of fuel and not air. I hope it is clear. In the next question we have, which of the following is not an air breathing engine? Turbofan engine, ramjet engine, rocket jet engine, turboprop engine. Can anyone tell the answer? C, rocket jet engine. Yes. So turbofan engine, you might know, turbofan and prop. In case of ramjet engine also, it doesn't have any moving parts, but still it will have a diffuser, a convergent divergent nozzle at the inlet, and then a combustion chamber, CV nozzle, sorry, CD nozzle, then a combustion chamber, and then again a CD nozzle. So this will increase the velocity. I think it will be the other way, because the inlet is Mach number greater than 1 for a ramjet engine, or maybe it is for the ramjet. So then with the combustion chamber, and then it goes out. So again air is involved in this in a ramjet engine. In turboprop, turbofan, it's common, but only in rocket jet engine we will have the combustion, the fuel and the oxidizer put into the rocket. Both are put into the rocket, so it can be either in solid form based on the engine, solid or liquid, or it can be like liquefied liquefied hydrogen plus liquefied oxygen in some cases. So this will not a rocket engine doesn't need any air for it to propel, because it will have its own oxidizer inside it. Which of the following aircraft engine has convergent divergent nozzle? Piston prop, turbo shaft, ramjet, turboprop. Answer C, ramjet. Yes, ramjet engine. Sorry, I think. Yeah, ramjet engine will have a convergent divergent nozzle because of the inlet and exit. It has to. It will deal with the supersonic flow, so it will have such nozzles. Other engines we know. In general, vertical climbing of turbojet aircraft engine is achieved using intercooler, afterburner, reheater, or multi-stage turbine. Vertical climbing of turbojet aircraft engine is achieved using intercooler, afterburner, reheater, or multi-stage turbine. So the answer is afterburner. We know that only afterburner is majorly used in turbojet engines. Turbojet engine will generally have a compressor, then a combustion chamber, and then a turbine, and then there will be an afterburner unit, and then a second turbine. Or it can be directly it will be fed to a nozzle in some cases. So this there will be some in this combustion chamber it will burn lean generally for complete combustion, but then at some operating conditions the air available at this point after the turbine will be very high. It is same as after the combustion chamber as well. So this air will be available in excess. So you can put secondary fuel. So this is fuel 1, and again you can put more fuel, and then use the available air for burning more and produce extra thrust. So this is done generally using an afterburner, and you can see that this nozzle can be oriented downward. They will have a mechanism to orient this downward and then have a vertical takeoff. So for vertical takeoff, the thrust or the thrust has to be very high. Thrust is generally the forward propulsive force, but while you climb vertically, then the force produced by the exhaust jet has to be very high, and this is achieved using afterburner. For a turbofan engine, maximum thrust is generated through cold nozzle, hot nozzle, fan or compressor. Yeah, yes. For a turbofan, maximum thrust generated is through cold nozzle. For a mixed turbofan engine, which mixture is expanded in conversion nozzle? Hot air and cold air fuel mixture after combustion, or hot air and cold air mixture after combustion, hot air and cold air and hot air fuel mixture after combustion, cold air and cold air fuel mixture after combustion. C, yes. Cold air and hot air fuel mixture, yes. So there will be two streams. There will be a fan, the center, and then you have a compressor, and then combustion chamber, and then turbine, and this air will be different and this air will be different at some stage. There will be a nozzle and this will be cold air, and here after the turbine it will be a hot air fuel mixture or the hot exhaust gas. So this gets mixed at this region, and so that is why the cold air and hot air fuel mixture get mixed. For ramjet and scramjet engine, the incoming air is compressed using axial compressor, centrifugal compressor, reciprocating compressor or oblique shock. D, yes, oblique shock. So these scramjet and ramjet engines will not have any moving parts. It can sustain only after it enters Mach number greater than 1. So before it reaches Mach number greater than 1, it will be propelled by some other engine and then put as it can act like a missile, so it can be used in a missile. So that missile will be thrown by some another engine or propelled by another engine, and once it reaches Mach number 1, this scramjet or ramjet can itself propel. So then it need not have any moving parts, and initially it can compress just by using oblique shock, and then it will have a combustion chamber and then a nozzle for propulsion. Which of the following is a correct expression for turbo machinery equation, where Cw is whirl velocity component, R is the radius of the shaft, suffix 1 and 2 represent the inlet and outlet condition of rotor. So the torque of the rotor is mass flow rate of the fluid multiplied by or divided by you have Cw2 into R2 minus Cw1 into R1. Yes, option A is right, because so we know that torque is change in angular momentum, and initial angular momentum, or this is rate of change of angular momentum. So initial angular momentum is given by m into Cw1 into R1, and then final angular momentum is m into Cw2 into R2. Now if you write torque is equal to you will have rate of change, so this m can become m dot or the mass flow rate into final angular momentum is Cw2 into R2 minus initial angular momentum we have Cw1 into R1. So that is expression 1a. In turbo machinery, what are the respective names of effect based on the change in kinetic energy due to absolute and relative velocity component respectively? Answer B is right. So change in kinetic energy is said as impulse effect for absolute velocity component, and then change in kinetic energy of relative velocity component is called as reaction effect. In general, centrifugal compressor is preferred for low volume flow rate, high pressure per stage, pressure rise per stage, high mass flow rate, or both low volume flow rate and high pressure rise stage. Option D. It is for when compared to axial compressors which has blades which are multiple stages, this consumes a very less space when compared to a centrifugal compressor. So if you want to have multi-stage centrifugal compressor, then each compressor will be like this. So the inlet will be axial through this, and then outlet will be radial. So then converting this, having multiple stages of this is very difficult, and also since it is having you can have change the radius, and then you can have very high pressure rise per stage, and you can see this area can be high when compared to the area of the impeller or the eye. This area has to be will be low when compared to the axial compressor. So then we can have only low volume flow rate for a centrifugal compressor. Stage pressure rise in centrifugal compressor with titanium alloy vanes is approximately dash times pressure rise as compared with aluminum alloy vanes. Yeah, answer is 2. It is 2 times. It can be higher because of the high strength of the titanium alloy, but it cannot be more. Centrifugal compressors are used in air separation plant for multi-stage up to 5 with intercooling, multi-stage above 5 stages without intercooling, multi-stage up to 5 stages without intercooling, and above 5 stages with intercooling. Yes, it is up to 5 stages with intercooling. I think this will be a part of your theory class. So in case of centrifugal compressor, impeller I is defined as from the top of the inducer to the top of the impeller, from the bottom to top of the impeller, from bottom of the inducer to top of the impeller, or from bottom to top of the inducer. So a centrifugal compressor will have a inducer, so that is, yeah, T is right. So this is the inducer, and this is the impeller. So from the bottom of to the top of the inducer, so this part to this part is called as impeller eye. The for centrifugal compressor, diffuser section reduces the velocity to a value which is around the same as the velocity at the inlet of impeller eye, diffuser, guide vanes or nozzle. Yeah, impeller eye, yes. So the objective is to just increase the pressure of the fluid and keep the velocity same. So that is why it will be as same as the velocity at the exit velocity of the compressor will be same as the inlet velocity of the compressor. So that is the inlet is happening at the impeller eye. So the velocity at the inlet of the impeller eye will be similar to the velocity at the exit of the diffuser. So diffuser, in the sense, it is the at the end after compressor, after the impellers. This is impeller eye, then you have diffusers. In thermodynamic analysis of a centrifugal compressor with the inlet guide vanes, which of the following statement is correct corresponding to the diffuser section? There is increase in stagnation temperature and decrease in stagnation pressure. There is decrease in stagnation temperature and pressure. Stagnation pressure increases and stagnation temperature remains constant. Stagnation pressure decreases and stagnation temperature remains constant. D, yes. So the enthalpy of the fluid remains the same. So that means the stagnation temperature is the same. T01 is equal to T02. However, the pressure decreases because of the diffuser, or the stagnation pressure decreases. Consider the following equation. Please choose the correct expression for P. Slip factor is, so slip factor is given by sigma, generally written as sigma, is Cw2 divided by P. So here P is the blade velocity. Yeah. So sigma is Cw2 by blade velocity. So this says with respect to the blade velocity, the outlet will velocity should have been ideally it should have been W in ideal case. Cw2 is equal to W, but in actual Cw2 will be less than U, and that is given by this factor sigma, or the slip factor. So now I have a problem. Before starting with the problem, I will just take a small break. Meanwhile, you can also have a break, or you can have a look at the problem. I'll maybe come back in maybe 2 or 3 minutes. Okay, you can start with the problem. The following data are suggested as a basis for the design of a single-ended centrifugal compressor. The power input factor is given. Power input factor psi is given as 1.04. Slip factor is sigma is 0.9. Rotational speed n is 290 revolutions per second. Overall diameter of the impeller is 0.5 meters. I tip diameter is 0.3 meters. I root diameter is 0.15 meter. Airflow mass m is given as 9 kg per second. Inlet stagnation temperature T01 is 295 Kelvin. Inlet stagnation pressure P01 is 1.1 bar. Isentropic efficiency eta C is 0.78. So the requirements are to determine the pressure ratio of the compressor and the power required to drive it, assuming that the velocity of the air at inlet is axial. So we can assume an axial inlet air entry, and then find the pressure ratio of the compressor and the power required to drive it, assuming this. And the second stage of the problem is to calculate the inlet angle of the impeller vane at the root and tip radii of the eye. Both angles has to be found, assuming axial inlet velocity is constant across the entire annulus. So this is the second part, and that part is to estimate the axial depth of the impeller channels at the periphery of the impeller. So now we know we can calculate the impeller tip speed. So this is pi into impeller tip is impeller tip radius is given as 0.5, so pi into 0.5 into revolutions is 290 revolutions per second, and can you calculate the tip speed? This is pi d into revolutions per second, so we will get the circumferential speed. It is 455.5 meter per second. Now the change in enthalpy can be given as of the total compressor and the diffuser together. So T03 minus T01. Only at the impeller there will be some change in enthalpy, stagnation temperature, because after the diffuser it is the enthalpy remains same, only the in the diffuser section only that velocity height will convert to pressure height. So till then, so T03 minus T01 is given by the total energy Cp divided by Cp. So we will also first see the energy imparted on the kinetic energy imparted in the let's say it is here. It has to be here because we will consider gamma as 1.4. Or we will write fluid. So that is equal to now we know sigma or the slip factor is sigma is Cw2 by U. This means Cw2 is equal to sigma into U. Now we will have kinetic energy is equal to sigma into U square. So this is the energy imparted per mass. So how this comes is we will have the change in angular momentum. So as we saw earlier, is equal to Cw2 into R. Right. So minus Cw1 into R. Initially we can assume that it is the inlet is radial, so this becomes 0, and then we will have only this, and this is so we have change in angular momentum multiplied by the omega will give us power. So change in angular momentum is into C1W2R into omega. So now R omega will become U. So U is the blade tip velocity. So that is how we got power as this one. So this is power per unit mass, and now we got kinetic energy imparted as Cw2 into U, and we have use sigma to replace CW2, and then we have power factor, which represents other losses, such as this represents losses on mechanical friction. Voltage loss, etc. So now the torque required can be given as this expression, or sorry, the energy enthalpy added to the gas. Now we have T03 minus T01 is equal to pi sigma U square divided by Cp. We know psi is 1.04 into sigma is 0.9 into U we have just calculated, which is 455.5 square divided by Cp. Cp of gas is 1.005. So everything has to be in SI units. On the numerator we have the meter per second in SI units, so denominator should also be in SI units. So Cp will become 1005. Can you calculate the change in temperature, stagnation temperature? Yeah, 193 Kelvin. Now we can calculate the change in stagnation pressure. This is given by 1 plus this isentropic efficiency of the compressor into T02 minus 3 minus T01 divided by T01 whole power gamma by gamma minus 1. So this is 1 plus this compressor efficiency is 0.78 into the change in stagnation temperature is 193 divided by T01 is given in the problem. T01 is 295 Kelvin. We can assume 1.4 as gamma, then we will have 1.4 by 0.4. Can you calculate the pressure ratio? Yes, it is not in bar, it is 4.2 because it is pressure ratio. But P01 is given, which is 1.1, so we can calculate P02. So sorry, P03. P03 is 4.2 into P01, which is equal to 4.2 into 1.1. Can you calculate this? Yeah, 4.6. So these are only stagnation pressures, these are not the static pressure. So this will have the velocity head component into it. Now we can calculate the power required. Power required is equal to mCp into the change in the stagnation enthalpy, which is T03 minus T01. Here m is given as 9 kg per second and Cp is known as 1.005 into change in stagnation temperature is 193 Kelvin. So with this we can calculate the power. Yes, it is approximately 1746 kilowatt. So we have calculated the pressure ratio of the compressor and also the power required to drive assuming is also found. Now next is to find the inlet angle of the impeller vane at the root and the tip area of the eye. So for this we need to understand the velocity triangle. So when at the inlet of the compressor, which is axial, the blade velocity goes from left to right, whereas the fluid velocity is axial, which is represented by CA1, and this is represented by UE. And then you get a this is UE blade velocity and CA1, which is the fluid inlet velocity, and then you get a relative velocity represented by V1. So this happens at the inlet. Similarly, at the outlet, you have the velocity coming out at an angle represented by C2. It will have two components, the radial outlet component and the well component. So for simplicity, we can assume that the outlet velocity, the radial velocity is equal to CA1. This will be used for the calculation of the mass flow rate through the impeller or something. So this mass flow rate to the impeller can be set as rho A CA1 if the density is at 1. Yeah, this also 1. And this is the well-in component, which is tangential to the blade, and this is the responsible for the angular momentum, which represents the angular momentum that is imparted to the gas. And because of these two, we have a actual velocity of the fluid represented by C2. So now at the inlet, we need to calculate CA1 to calculate the vane angle. This U is known because we know the tip velocity and the tip velocity, not actually the tip. We at the both the eye and the tip and the root velocity we can calculate using the diameter and the velocities, but this CA1 is not known. If CA1 is known, we can calculate the vane angle. This angle you can say is alpha. So to calculate this CA1, we know that M is somehow related by rho and the CA1 axial velocity, which is the flow rate is related with this, but here rho1 is not directly known. We know T01 and we know P01. These are given, but and m dot is given, but velocity is not given, so we have to find it iteratively. So you know T01 is equal to T1 plus C1 square by 2Cp, and similarly you can calculate for the pressure also. So using all these expressions, you have to iteratively find the CA1 or the inlet axial velocity. These problems are just for understanding. Mostly the entire problem cannot be asked in NPTEL exam or something, but this will give a good understanding of how things work. So first we can start by calculating the area 1. Area 1 is pi by 4 d square minus d square, the tip diameter divided minus the root diameter. So we know pi by 4 tip diameter is given by 0.3 meters and root diameter is 0.15 meters. So we have 0.3 square minus 0.15 square. So can you calculate the area? It is 0.053 meters square. So now how do we go about this is we will find the row 1 based on P01 and T01 using row with m equal to rho 1 a ca1 expression. We can calculate ca1, and then this ca1 we can calculate with this. We can calculate t1 because t1 is t01 minus c1 squared by 2cp, right? Then if t1 is known, we can calculate p1. How? We know p1 is p01 divided by t01 by t whole power gamma by gamma minus 1. Now with this knowing p1 and t1, we can calculate rho 1, which is a function of p1 and t1, and we can verify. And with this rho 1, you can again using m dot expression you can calculate ca1 from m. Now we can verify if this ca1 is same as the ca1 we have obtained at this step. Maybe this is first step and this is second step. Then we can see if both are matching. If it is not matching, then we can use the second finally obtained ca1 and again start this calculation again. Put here, calculate t1 p1, and then we can finally end up with some converged value of the ca1. So to start with, we need to calculate some some initial guess has to be very close to the final value so that you will converge soon. So for this, we will assume rho 1. We can calculate rho 1 from P01 and T01. We will say rho 1 is P01 by RT01. P01 is given the problem, which is 1.1 bar, and T01 is 295. So it is 1.1 into 10 power 5 divided by R is 287 into T01 is 295. So with this we can calculate rho 1. So these are just the assumed value of rho 1, not the final value. I think it is 1.3. So it is 1.3. I'm getting 1.29923, so I will write it as 1.3 bar. Sorry, 1.3 kg per meter cube. So this is rho 1. Now we can, with m equal to rho 1 a1 ca1, we can calculate ca1 as m by rho 1 a1. We know m in the problem is given as 9 kg per second. So we will have 9 divided by rho 1 is 1.3 into area. We have calculated it as 0.053. So we can calculate ca1. 130.62. Now we know CA1. We can calculate the velocity head, that is CA1 square by 2CP. This is 130.62 square divided by 2 into 1005. So this is 8.48. This will have the unit of Kelvin. Now we have T1 is equal to T01 minus C1 square by 2Cp. So this is T01 is 295 Kelvin given in the problem, and minus C this term we have just found it as 8.48. So now T1 can be calculated. $286.53. Yeah. Now T1 is known. We can calculate P1. P1 is P01 divided by this expression. So P01 is 1.1 into 10 power 5 divided by T01 is 295 divided by 286.53, the whole power 1.4 by 0.4. So this is P1. Can you calculate the value of P1? Okay, 0.99 bar. So now we can calculate rho 1 again. So rho 1 is P1 by RT1. So P1 is 0.99 into 10 power 5 divided by R is 287 into T1 we have just calculated it as 286.53. So now rho 1 can be calculated. So this is 1.203 kilogram per meter cube. So rho 1 is, earlier it was 1.3, now it has become 1.203. Now with this we can again calculate CA1, which is m by rho 1 A1. M is 9 divided by rho 1 is 1.203 into A1 is 0.053. This is 141.1 meter per second. So now we saw earlier we got CA1 as 130.6 and now we have got 141. The variation is very high, so we need to iterate again. With CA1 we can calculate again the temperature head, that is CA1 square by 2CP, which is 141.1 square divided by 2 into 1005. So this is 9.9 Kelvin. Now we can calculate T1 as T01 minus C1 square by 2 Cp. This is 295 minus 9.9. Should be 285, 85.1 Kelvin. So now T1 is known. We can again calculate P1, which is P01 divided by T01 by T1 gamma by gamma minus 1. We had 1.1 into 10 power 5 divided by 295 divided by 285.1 power 1.4 by 0.4. This is 0.976 per 0.976 per. Now rho is P1 by RT1. We have 0.976 into 10 power 5 divided by R is 287 into T1 is 285.1. 1.192 kilogram per meter cube. Now CA1 is m by rho 1A1 9 by 1.192 into 0.053. $142.45. So earlier we started with this value of 141. Now we have got we started with 141.1. We have reached 142.45. So earlier before this stage it was 130 to 141. The difference was 111 meter per second. Now it has become around 1.3 meter per second. Maybe we will just do one more time and finish it off. Maybe this is sufficient for this. So CA1 is known. Now I calculate T1 again. T1 is T01 minus C1 square by 2 Cp, which is 295 minus 142.45 square divided by 2 into 1005. $284.9 Kelvin. So this is very closer to the previous value, which was 285.1. So we are converging. P1 is P01 divided by T01 by T1 power gamma by gamma minus 1. This is 1.1 into 10 power 5 divided by 295 divided by 284.9, the whole power 1.4 by 0.4. Okay, 9737 bar. So this is 0.9737 bar. Now we can calculate rho 1, which is 0.9737 into 10 power 5 divided by 287 into T1 is 284.9. So row 1 is this is 1.19 kilogram per cube. Okay, earlier we have got 1.192. Now CA1 is 9 by 1.19 into 0.053. Okay, so this is 142.69 meter per second. So this is much closer to the previous value, which is it is only 0.45 and 0.69 variance of this. So 0.14 meter per second is the error. So now we can calculate the blade vane angles. To calculate the vane angles, as I said, we need to know the tip velocity and the root velocity. Now tip, that is impeller I tip velocity. Tip velocity is given by pi into 0.3. I tip the diameter is 0.3, so we have pi into 0.3 into the rotational speed, that is 290 revolutions per second. This is 273.31 meter per second. Yeah. Similarly, we have I root velocity, which is pi into 0.15 into 290. One 136.65 meter per second. So we have got the velocities. We can calculate the angle, vane angles. So alpha at root is equal to tan inverse of 143 by 36.5. Okay, yeah, sorry, this is at root. Yeah. 46.33 degrees. Similarly, alpha at tip is tan inverse of 143 by 273.31. .61 degrees. Yeah. So we have as in the problem, we have calculated the inlet angle at the impeller range at the root and tip radius we have calculated. So the next one is to estimate the axial depth of the impeller channels at the periphery of the impeller. So axial depth at the periphery of the impeller. Please think how we can solve this. I will be back in 2 minutes, or you can also take a break. So the third part of the problem is to estimate an axial depth of the impeller channels at the periphery of the impeller. So for this we need to calculate the density at the impeller tip. So we can assume that as I said, the radial outlet velocity is equal to the axial velocity is an assumption that we make. So that means CR2 is equal to 143 or 142.69, which I have approximated to 143 meter per second. 143 meter per second. Now CW2 is sigma into U. Here U we haven't calculated it, or no, we have calculated initially. So sigma is 0.9. Yeah, sig factor sigma is 0.9, and the impeller tip velocity is calculated as 455.5. So this into 455.5. So this we can calculate CW2. (409.95 meter per second). Now can calculate the C2 square by 2Cp for the outlet condition. So this is Cr2 square plus Cw2 square by 2Cp. This is Cr2, we have assumed as the inlet condition, that is 143 square, plus Cw2 is known, that is 409.95 square, divided by 2 into Cp is 1005. .78 Kelvin. So now we can make another assumption that the inefficiency 0.5 times the inefficiency of the isentropic inefficiency is 0.11. Now then we will have P02 by P01 as 1 plus 0.89 is the isentropic compression, isentropic efficiency into T03 minus T01. This we have calculated earlier. I will write this one and 295, or this is T01 whole power gamma by gamma minus 1. This is 1 plus isentropic. So then with this we will calculate, we will get efficiency as 0.89, 1 plus 0.89 into the difference in the enthalpy we have calculated earlier as 193 divided by the intake stagnant temperature is 295 whole power 0.4 by 1.4 by 0.4. P02 by P01 is 4.98. Now we can calculate P2 by P02, which is T2 by T02, the whole power gamma by gamma minus 1. T2 is known. Yes, T2 is T02 minus, we didn't calculate T02, right? Okay, first T02 is equal to T03. As we saw earlier, in the diffuser state there won't be any change in the stagnant temperature, so that means it is same as T03. T03 we have calculated here from this, right, is same as T03, which is 193 plus T01, 193 plus T01, so that is 193 plus 295. So this is 488 Kelvin. So 488 Kelvin is the stagnation temperature at second state and third state. Now we have this expression T2 equal to T01 minus C2 square by 2Cp. This is yeah, we have calculated here. So it is 488 minus 93.78. So with this we can calculate T2. (394.22 Kelvin). So this is T2. Now P2 by P02 is T2 by T01 we saw earlier, so that is 393.4.22 divided by T02 is 488 the whole power 1.4 by 0.4. So this is 0.473. Okay. Now we know this P2 by P02, and then we know P02 by P01. So P2 by P02 is 0.473, whereas P02 by P01 is this is 4.98. Now we can calculate P2. So P2 is 0.473 P02, and P02 from this expression is 4.98 P01, and we know P01 is 1.1 bar. So we can calculate P2 with this. $2.595. So now we know P2 and T2. So with this we can calculate rho 2. So rho 2 is P2 by R into T2. P2 is 2.595 into 10 power 5 divided by R is 287 into T2. T2 is we have just calculated here, it is 394.22. 394.22. So we can calculate rho 2. This is 2.293 kilogram per meter cube. Yeah. So now we know rho 2, and we can calculate the area required for the mass flow rate. So we know this is rho is m by rho 2 into C2. So this is CR2. Because it is radially going outside and we are calculating the periphery area. So this is 9 divided by rho 2 is 2.293 into CR2. We assume it to be the same as the inlet air velocity at radius. So this is 0.027 into square. So now we can find the depth of the channel. this is 0.027 divided by pi into 0.5. The circumference is pi into 0.5 because the tip impeller tip radius or diameter is 0.5. So now the depth of the channel can be calculated. .017 meters, or it is 117 centimeters, or not, sorry, 1.7 centimeters. So I will just if you have any questions you can ask, or I will just go through the problem again, summarize the problem. Pi into 0.5. So at the outlet, so this is a compressor, right? So centrifugal compressor. So there will be a depth here. So now we need to calculate this depth, and we know at the tip, for the tip density and the tip velocity, we know what is the area, entire area that is needed, that is A2, because the air has to flow through all this area, and we know the this circumference is given by, this is given is 0.5 meters. So we have got this depth, maybe this is as t, then we have A2 is equal to pi into d into the diameter is 0.5. So you have any other questions? I will just go through the problem once. We were given some specification for the centrifugal compressor, like the slip factor, power factor, rotational speed, overall diameter of the impeller, the eye tip and root diameter, air mass flow rate, inlet stagnation temperature, inlet stagnation pressure, isentropic efficiency. These are given, and we are asked to find the pressure ratio of the compressor, power required to drive, assuming the velocity of the inlet air is pure axial, and then to calculate the inlet angle of the impeller vanes at the root and tip radii of the eye, and again this is assuming inlet air velocity is constant across the eye annulus, and to estimate the axial depth of the impeller channels at the periphery of the impeller. So the impeller tip speed can be calculated using the impeller tip radius and the rotational speed, and we have calculated it as 455.5, and the change in stagnation temperature can be calculated by finding the kinetic energy that is imparted to the gas divided by the Cp, and kinetic energy imparted comes from based on the slip factor and the power factor into the blade tip velocity square. So we have calculated that as 193 Kelvin, and with this we can also calculate the pressure at the third stage. So that is the pressure ratio between the first and the third stage, third state, and that is 4.2. And this we know P01 stagnation pressure at the inlet. So with that we can calculate the stagnation pressure at the outlet, which is 4.6 bar. Now the power can be calculated as mCp into delta T. Delta T is the difference in the stagnation and temperature here. So we have calculated it as 1746 kilowatt. Now we need to calculate the angle at the vanes. So for calculating the angle at the inlet vane, we need to know the axial velocity. So from this triangle, velocity triangle, we know the blade velocity, we don't know the axial velocity. If axial velocity is known, we are using tan inverse, we can calculate the angle alpha. So to calculate CA, we know only the stagnation conditions at the inlet, and the mass flow rate is also known. With this, we have to iteratively find the inlet axial velocity, and this area can be found because the I tip and root diameters are given. So with this, we have calculated the area as 0.053 meter square. And so now how we proceed, the flowchart is given here. First we will assume some density at the inlet. This is using assuming that the stagnation and static pressure and temperature are the same. Then we will calculate some rho 1, and this we are using this, putting into continuity equation, that is m equal to rho 1 a ca1, we can calculate ca1, and this can be with this and the stagnation temperature, we can calculate the static temperature, and then using the expression between the pressure ratio between static and stagnant and the temperature ratio between static and stagnant, we can calculate the static pressure at the inlet. With the static pressure and static temperature, we can calculate the density, and again using this density we can calculate the CA1 using the expression from m. And now this CA1 we can again put back into the temperature, static temperature calculation, and then we can repeat this loop. So in the first we started with rho 1 of 1.3 kilogram per meter cube, and then we got CA1 of 130.62 meter per second. After the at the end of first iteration, we have got it as 141.1 meter per second. So the difference in the starting value at the end of the iteration, we have got it around 11 meter per second. So we continued for the second iteration, and then we found that it is at the end of second iteration we got around CA1 of 142.45, and at the end of third iteration we have got it around 142.69. so we have stopped at this point, and we have calculated the tip velocity, I tip velocity and I root velocity of to be 273 and 136 meter per second. With these two values and the axial inlet velocity, we can calculate the vane angles, which is 46.33 and 27.61, and then we want to calculate the depth at the outlet. So for the calculating depth at the outlet, we need to calculate the density at the outlet. So for this, we started with assuming radial velocity at the outlet is same as the axial velocity at the inlet, and with this we got CR2 as 143 meter per second, and using the slip factor and the blade velocity, we got well velocity as 409.95 meter per second, and with the C2 by Cp square, that is a velocity head at the outlet, is calculated as 93.78. Now we made some assumption for the compression, and that is around 0.89, and then we calculate the ratio between P02 and P01, which was 4.95, and then we calculated the P2 by P02 ratio, which is 0.473, and with these two ratios we finalized the value of P2, which is 2.595 bar, and we already calculated T2. With these two values we can calculate rho 2, which was 2.293 kilogram per meter cube. With this we can calculate the area required at the outlet, and we know the diameter of the outlet, so we have finally calculated the depth of the channel. So maybe the entire problem as one single unit you may not encounter in an NPTEL exam. Maybe some parts of this can be asked. So if you have any questions in this problem or any other problem, you can ask me. Or if you have any other problem that you think that I need to solve or explain, we can look into it. Maybe if not this, if I know the solution, I can solve and show you this time. Otherwise I can also take up and solve it in the next class. So Mr. Steve, okay, you can unmute. I just want to know about you. You are a regular BTech student or BE student and doing this course, or you are a working professional, or okay, I can unmute. Okay, actually, no, I also cannot unmute. Okay, so you can maybe type in here. You are a bachelor student. Okay. Where are you studying? University, third year. Okay. I just want to know how people. Oh, Kumaraguru College of Technology. So, okay, you must be from Tamil Nadu then. I am also from Tamil Nadu. Okay. Okay. And is this part of your course? Maybe based on this NPTEL score, you will get the CGPA for your BE certification, or you are just doing out of your own interest? No, okay, only for others. Okay. So, if you have questions, we can ask, or we can close the session. Are these sessions helpful for you, or you are just calculating the numbers? I think you have answered almost all the these questions, also objective questions. Yeah, okay. Yeah, good to know. Thank you. Okay. Okay, fine. So if you don't want to tell anything, yeah, we can close the session. Thank you.